back. Hi. A little sleepy today, huh?
Caked out.
You're caked out. Too much cake?
Yes.
Too much cake. I'll save you from it.
I want more.
Oh. But
Hey.
Happy birthday!
Thank you. I'm getting high.
okay, so like I was saying right before I kicked on the recording, we've been talking about triangles. Today, we're going to talk about inequalities inside of a triangle. Now, a lot of you guys know how to do what we're about to explain real intuitively. And I know this because when we've been doing our conversations on congruent triangles, I'll go, okay, well, which sides are congruent? And some of you have said, oh, these two definitely aren't. And I'm like, well, how do you know? And a lot of the times you say, oh, because the angles are different sizes. And my first response had been, you're not wrong, but we can't say that yet. We can't use that as the reason for congruent or not congruent, is the size of the angles, because we didn't have that information yet. Today, we get that information in the form of some angle-side relationships. But first, let's remind ourselves on how inequalities work. We have three properties of inequalities that we are already familiar with: transitive, addition, and subtraction. The transitive property for inequality works exactly the same way as the one for equality and for congruence. And it looks something like this. Say he's got some pencils, okay? We gave him some pencils, he's got pencils. But he has fewer pencils than she does, birthday girl. But birthday girl has fewer pencils than he does. Which means the dude in the back has less pencils than he does. Right? This is transitive property. Addition property is going to work the same as your used to addition property has. Okay? Two of you have some pencils. Okay? You've got pencils and you've got pencils. You have more than she does. Yes? I give both of you the same number of pencils. You still have more pencils than she does because I gave you guys the same number of pencils. Right? And subtraction is going to work the same way. You've got fewer pencils than he does. I take away some pencils. You still have fewer pencils. Make sense? So the property that's new in terms of the name of it is the comparison property. The comparison property of inequality is the property that allows us to look at two numbers and say, well, Bob, there's only three possible choices. One of the numbers is less than the other number. Both of the numbers are the same as each other, or one of them is bigger than the other.
Isn't that the same as one is smaller?
Yeah, it's just reversed in a different order.
It's like the column versus.
Mm-hmm. Which means that we can't use symmetry. Remember our symmetric property? Where it allowed you to flip the two sides and everything was happy and fine and no one really cared? We care when we get to inequalities. We can't just flip them. Okay? If we want to change the sides, we have to flip the inequality symbol too. Okay? All right. Which is all well and good. Nothing seems super complicated. And in fact, nothing exciting really happens until we get the exterior angle involved. We talked about the exterior angle once already. We did that way back here in 4.2 when we looked at this theorem. Remember this theorem? This is the one that said if I've got a triangle and some angle hanging out outside, knocking at the door, trying to get into the triangle party, its measure is equal to these two angles added together. But listen to how we said that. The measure of this angle is equal to these two added together. The new theorem that we have today, the exterior angle inequality theorem, says that if I look at this exterior angle and I compare it to just one of these remote interiors, say this one, that exterior angle has to be bigger than that. Which makes sense. Because in order to get the measure of this angle, I have to take this one and add to it this other one. Which means it has to be smaller than the exterior. Make sense? And so that is what this theorem, the exterior angle inequality theorem, says. The measure of the exterior angle of a triangle is greater than either one of its two corresponding remote interior angles. So this guy hanging out here is bigger than this guy. And it's also bigger than this guy. Now, I don't know how those two remote interiors work with each other. Like, I don't know that. They could be congruent. One could be smaller than the other. Could be the other way around. I don't know. But I know that whatever those measures are, they cannot be bigger than this one. This one has to be the biggest. But I started off the conversation today saying that we were going to give you the power now to state that sides are bigger than other sides, or at least not equal to, based off of angle measures, and vice versa. And in order to do that, we're going to use angle-side relationships. When you're done, flip the page and we'll start with what those relationships are. The angle-side relationships in triangles are both theorems. They've got some fancy numbers. It's fine. For the reason if you're calling on one of these theorems, just write it out what you're thinking. They don't have any fancy names. The first one says this: if one side of a triangle is longer than another side, then the angle opposite the longer side has a greater measure than the side opposite than the angle opposite the shorter side. I'm sorry. If one side of a triangle is longer than the other, then the angle opposite the long side is bigger than the angle opposite the small side. Sorry about that. So this one, you are required to start with sides, and it tells you something about the angles. So I'm going to look here in this little picture so that we can visualize it a little better. I've got this side, and I'm being told that this side's measure is 9, and then I have this other side, and I'm being told that its length is 7. Now, if this side is 9, and this side is 7, which side is bigger? The pink one or the blue one? The pink one, because the pink is 9 and the blue is 7. That means that the angle across from the pink side, this pink angle, is going to have a bigger measurement than this angle across from the 7. It doesn't tell me what those measurements are. I have no way of saying, oh, well, when it's a side length of 9, the degree is, no, I can't do that. But I can at least give some sort of comparison. It's going to be bigger than the other. The other theorem is the exact same thing, but it goes in the other direction. If I know the measures of the angles, and one of the angles has a greater measure than the other angle, then the side opposite the greater angle is longer than the side opposite the lesser or the smaller angle. Okay. So this one's, you're going to start with knowing something about angles and being able to make a determination on how the sides compare to each other. Let's look at the diagram. Here I have some diagram. This angle right here at J measures 110 degrees. And this angle here at K measures 45 degrees. What does that let me say about the size of the sides opposite each of those angles? Which side is bigger? KL, the one across from the 110 degree angle, because 110 is bigger than 45, and so the side that is opposite the 110 angle has to be bigger than the side opposite the 45 angle. I don't know how long those sides actually are. Perfectly timed bell. I don't know how long those sides actually are. I don't have a way yet to use angle measure to give me side length. Note the word yet. But I can say now which one will be bigger than the other. Okay? Let's use that to do at least 2 or 4. So the directions say use the figure to the right to determine which angle has the biggest measure. All right, I'm looking at angle 4, which is right here. I'm looking at angle 8, which is right here, and angle 9, which is right here. Which one is the biggest? 9. Someone was about to say 4 and then stopped because they were worried that they were wrong. Someone else might want to say 8. And then a few of you might go
I'm dumb. It's 4.
4 because it just looks bigger, right?
I think 9.
I think
Because of the exterior angle. Which,
Yeah, remember that you can't rely on, oh, it just looks bigger, because this triangles could be drawn not to scale, so you have to use position. If I look at the triangle I just colored, and 4, is 4 inside the triangle or outside? Outside, so it's an exterior angle.
Wait, did you say 4? Wait, you said 4 is outside thing?
4 is outside the triangle that I colored.
Oh.
Okay? It's not sitting inside the yellow. It's bright yellow, it's not dark yellow. So it's an exterior angle. So if I look at these angles out here, those are the remote interiors. We had a theorem, the exterior angle inequality theorem,
is greater than
That-
the 2 counterparts.
that said that that exterior angle is, as you said, greater than either one of those 2 remote interiors.
So 4 is actually greater.
So 4 must be the greatest angle. I don't know how 8 and 9 are related, but I know that 4 is bigger than 8 and 4 is bigger than 9, so 4 is the biggest out of all 3 of them. Do you want to see another example?
Wait, so
Yes.
then the triangle, they're like, we have to go by, because you know, you said that you don't make them the right size.
Yeah, I'm not making a statement about what the actual measures of the angles are. I'm just making a statement about how they relate to each other. And you can make that statement with this position, the fact that this is an exterior angle and these 2 are the remote interiors. And we had this theorem that we just looked at a little while ago that said that if we've got this setup, the exterior angle is always going to be bigger than this one, and it's always going to be bigger than this one. Because of a previous theorem that said in order to get this measure, we have to add these 2. Yeah? Do you want to see on this one? Yes? Okay. So I need to look at 7, 8, and 10. Here is 7. 8 is already colored in pink. And I'm going to color angle 10 in green so we can see it. There's angle 10. Which one's the biggest? Why?
Because it's the exterior angle of 7 and 8.
Because 7 and 8 are the remote interiors, angle 10 is an exterior angle, and we have our inequality theorem. You guys are absolutely correct. Did you see it? Came easier this time, yes? Very nice.
These do not have these. These 2?
Those 2, no, because I looked in the textbook and they just have numbers. It's like 5 point, and I was like, you know what, forget it. Just collectively, they're the angle side relationship theorems, and You've got one that goes side to angle, one that goes angle to side. They don't have cool names.
So we just write that as the name, angle side theorem, side angle theorem?
Yeah, oh, okay. In order to give these names, the suggestion, in case you missed it, because I saw a couple people's eyes go, what? In case you missed it, the suggestion is being made to name these theorems. Since this one goes side, then angle, to name this one the side angle relationship,
Yeah.
and then to name this one the angle side relationship. I'd be okay with that. That wouldn't, that looks like a P. That wouldn't bother me at all, if that's what you wanted to do. I'll make a note here. And of course, I'm abbreviating relationship like hardcore. Okay. Let's do this next example. We're using the exterior angle inequality theorem again. So bust that one out and have that sitting next to you so you can look at it. And we want to use that to list all the angles that satisfy this stated condition. And the condition is that we need things less than the measure of angle 1. So we need things whose angle measures are smaller than that.
3 and 4.
All right, 3 and 4. So he looked at this triangle, identified that 1 was exterior, which meant 3 and 4 were the remote interior. And so the measure of angle 3 is less than angle 1, and the measure of angle 4 is less than the measure of angle 1. Are there any others?
Probably. For now, I think those are the only ones that we can prove.
Okay. Well, what if I looked at this triangle?
Well, then it would be 5 and 4.
5 and 4 with this little added piece that I don't have a name for, so I'm just going to ignore it for now.
Yeah.
But you're not wrong.
And then if we did the entire triangle, it would be 8 and 7. So man, number 1 must be pretty big.
Did you see it? So we looked at the first little tiny triangle, and then we did the next biggest triangle. Now we're doing the entire triangle, which means now 8, and this entire angle right here are the remote interiors. And since this big angle is made up of angle 4, this one I don't have a name for, and angle 7 has to be smaller than all of these combined, which means it has to be smaller than angle 1.
Those really aren't drawn to scale.
No, they're totally not.
So we can't just look at it and say, oh, it's smaller.
Right. You're not allowed to go, it looks smaller. So I couldn't state right now that angle 2 is smaller than angle 1. It definitely looks smaller because of the way it's drawn, but I don't have a theorem that tells me that. At most, I could state that their measures added up to 1/8. But unless I knew some measures, that's all I could say. Okay. Do you want to see another example, one of these other 3? I heard yes? Okay. If you don't, you can start playing with the, what's it called?
5-3.
Yeah, the 5-3 assignment, as I flip through here and try to find another thing that isn't all colored on the way this one is. I kind of went color crazy earlier this morning. Okay, so here's one that isn't as colored on. Let's do, you pick 6, 7, or 8.
7.
7, okay. So measures greater than angle number 7, so I need to find number 7. There's number 7. I want things bigger than that one. Okay, well if I look at this triangle for number 7, bless you, where are its exterior angles?
9.
9 is totally an exterior angle, so it has to be bigger than 7. Which other one? We're looking at this triangle right here, right now. We had 9 as an exterior angle. Where is there another exterior angle?
1.
Yeah, we could come back over here and do this big one, right? and say that 7, since it's part of this angle, and this entire thing is a remote interior and it's smaller than 1, 7 is smaller than this big thing, so 7 has to be smaller than 1. Yeah, you could say that also. Is there another angle that's bigger than 7? Having trouble seeing them, yeah? Okay. Well, let's look at the purple triangle right now, which angle 7 is the dark purple smudge I'm about to make. There is number 7, that super dark purple smudge. Is this an exterior angle to that triangle?
Yes.
Yep, it's hanging out outside. Is 7 one of its remote interior partners? Meaning, is 7 inside of the triangle this is next to? Yes. And is it not next to 5? Yes, it's way over here. Which means 5 is an exterior angle, and so it must be bigger than 7. So there's another one. What if I looked at this triangle? That big green one. Is 3 an exterior angle to the green messy triangle? Yes, which includes all the way into the purple part, yeah? So yes. Now 7 is still this dark smudged one out here. This is still angle 7 right here. 7 is now part of this big angle, which is the remote interior to number 3. Which means number 3 is bigger than this. But 7 is a part of this, so 7 must be smaller than this whole thing, which means 7 must be smaller than 3. We're using that transitive property, kind of leapfrog, checkers board our way across. Did you see it?
I did not see it, but I didn't.
You did not say,
I
like,
thought you just said 3 was smaller than 7.
it's bigger. What did I say? Because 7 is a part of this angle, and this angle is a remote interior to 3. This entire thing is smaller than 3. And since 7 is a piece of this, 7 has to be smaller than 3.
Oh.
And so 3 has to be bigger than 7. Okay. This one's real easy to overthink. All right, let's look at the next page. This one is going to be using our angle side relationships and our side angle relationships. Use the figure to the right to determine the relationship between the measure of the given angles. So we want to know the relationship between the angles, and so we need to be given information about the sides. All right, I'm looking at angle RTW. Start at R, go to T, turn around, go to W. RTW then is this angle, and opposite that angle is this side, measure 34. The next angle is angle TWR. TWR, that's this angle right here. And across from that angle is a side that measures 35. Those are not the measures of the angles. Those are the measures of the sides related to those angles. Between 34 and 35, which one's bigger? 35, which means that the measure of angle RTW is smaller than the measure of the angle TWR. Or you could say that the measure of angle TWR is bigger than the measure of angle TRW. It's totally the same thing. You only have to write it for one way, and it doesn't matter which way you write it. Did you want to see the other one? Number 12? Do you want to see this one again?
Yes, please.
Yes? Okay. So I'm looking at angle WQR. I'm going to start at W. I'm going to go toward Q. And then I'm going to turn and go toward R, so I'm talking about this angle here. The side opposite that angle is this side with a measure of 34. This angle, QRW, start at Q, go toward R, turn around and go toward W. That's this angle right here. And across from that angle is this side with a measure of 45. Between 34 and 45, which one is bigger?
45.
45 is bigger. And so this angle is larger in measure than this angle. I still don't know what those angle measures are, but I know that whatever they are, this one has to be bigger than this one. And so we would write our relationships like that. Or if you wanted to, you could write it the other way. No one is going to stop you. Feeling okay with this? Better about it? Okay. Let's do this again, but this time we're going to say a relationship about the measure of the sides given measures of angles. Again, we're not going to be able to know what the side measurements are. I don't really know how long they are, but I can say something about how they relate to each other. All right, side DE, here is side DE. Opposite side DE is this angle whose measurement I don't know. It's right here. Sorry. Thank you. All right, so this angle right there, but I don't know its measure. But I notice that this entire triangle right here has an exterior angle. And according to our old exterior angle theorem, that measurement is found by adding these two remote interiors. Which means to figure out the measure of this missing angle, I can take the exterior angle and subtract from it the other remote interior. Someone help me. I got 65.
Yes.
Okay. So then this is related to an angle with a measure of 65. It doesn't measure 65. It's just related to that angle. Now we're going to look at side DG. Here is side DG. Opposite side DG is this angle right here, whose measure I don't know.
What can't you just subtract from 180?
I can. What am I going to subtract from 180? The 113, because I have a linear pair right here. Yes, sir, I can definitely do that. That's going to be the least amount of work for me.
How'd you get the top one?
How'd I get the top one? What? The blue?
Yeah.
This one?
Uh-huh.
Exterior angles.
Oh, okay.
These two add together. So if I subtract this thing from this thing, it leaves me with that thing. 67? All right, which one's bigger?
The DG.
The D to G. So then I can write that the measure of DE, notice how I wrote measure of the line segment DE. I just wrote the letters DE, there's no symbols involved. The measure of line segment DE is less than the measure of line segment DG. Yeah?
Hey,
Alright.
why didn't you put the measures?
You could. I suppose if you really, really, really wanted to, we could do that. But if we just remove the line on top, we don't have to put the M, and that's way easier. Whereas with an angle, if we got rid of the angle symbol, then are we talking about angles or planes or just 3 dots or I don't know, you know? At that point, we need the symbols. All right, the last example is a little baby word problem. It says the figure shows the position of 3 trees on one part of a disc golf course. Do you know what disc golf is?
Yes,
Yeah.
you know you throw, right?
Yeah. Do y'all know what frisbees are, right? Yeah. So what disc golf is it's frisbee golf. Okay, so picture a trash can, but now make it out of chains and put it on a stick. And put the stick in the ground so the trash can is about where your waist is.
Yeah, they didn't.
Huh?
Prisoners.
They didn't what?
Zoe 101. The
A TV
prisoners.
show.
Oh, TV show. Okay. I clearly don't watch television.
It's
I know.
like 10 years old. The show's like 10 years old.
I feel so old now. Thanks, guys.
Well, we were like 5 when we were.
And you still know what it is? You guys are amazing. The power of Netflix. YouTube. So you have these trash cans. They're made of chains, and you throw the frisbee at it and get stuck in the chain, and you get a point for every frisbee that's in your chain trash can. Yes? That's frisbee golf, also known as disc golf. So they're playing frisbee golf, and they've got 3 trees somewhere on the course as obstacles for you, and they want to know which position, at which tree position is the angle between the trees the greatest. Which side of this triangle has the longest distance?
The 53 feet.
The 53 feet is the biggest, so this side of our triangle is the longest.
And therefore angle 2 is the greatest angle.
Exactly.
That's all I want to know.
That's it. That's all they want to know.
I love TV.
The tree at position number 2. And that's all I had for you guys today. Thanks.
Outro.
Outro. Do you want to do it or should I?
Should I do it? Okay. Smash that like button, click that subscribe button, and we'll see you in the next
And if you hit the little bell when you're out sick or traveling for any of your extracurriculars, your phone will let you know when lectures been updated. Thanks, guys.